Okay, let's talk about 4.9 day 2 first. If this is our velocity curve, and we want to think about position in terms of it, what you need to do is think about what velocity looks like and what the corresponding position change would be. For example, if velocity is constant, then I know my original function is linear. So anytime I have a constant velocity, I know I'm going to have a linear change in position, right? So first, this is a constant and it's positive, so that's why it looks like this, right? This is zero velocity, so that means position doesn't change. And this is zero velocity, so that means position doesn't change, yes? Well, then my velocity here is increasing, yes, right? So since it's increasing, my velocity is increasing right there. I see that my position is increasing, right? Then we also see over here that my velocity is slowing down over here up to zero. So that means even though I have a positive velocity, it's getting smaller and smaller and smaller. That's why it's doing something like this going towards zero. So here I have a positive velocity and it's getting bigger. That's why it looks like this. Here I have a positive velocity, but it's going towards zero. That's why it looks like this. Now I have a negative velocity, and this is the most negative it ever is. So that's why it goes down like so to here. But then it's negative. That's the biggest it ever is. But then it goes back up like this to a zero velocity. That's why it goes like this. So the position stays there for a while. Okay, not easy at all. And we can talk more about stuff like that in class. Hopefully that kind of gives you some sort of an idea as to how those two are connected. So then 62, it says we accelerate like so. And here's our position and velocity. We take one antiderivative and get this. So a constant c pops out. But since velocity at 0 is 4, that means when we plug in 0 into velocity, we better get out 4. And I found out that c is 2. So I can put that back in our equation. And now here's my new velocity equation with that 2 plugged in. And so now I take an antiderivative and I get this. But notice a d pops out because we took another antiderivative. But since s of 0 is 0, that means we get out 0 when we plug in 0. So I think you quickly find that d ends up being equal to 3. And so this is our position function where we take that d equal to 3 and plug it in. When we come over here, if we have something that is 450 meters off the ground, then if we are falling, if we just drop an object, its acceleration due to gravity, this is something I would give you on a high-stakes test. An object neglecting air resistance falls at a rate of negative 9.8 meters per second squared. So if we take the antiderivative, that's going to be what we get, and a plus c pops out. Well, since we just let it go, we didn't throw it down with any velocity, our initial velocity is 0. So that means c is equal to 0. Because when we plug in 0 in for time, we better get out 0 for velocity. So c must have been 0. So this is our new velocity. So if that is velocity, then if I take one antiderivative, a d, constant d pops out. And so now if position is, time is 0, position is 450, that means it started 450 meters up in the air. So when you plug in 0, you get out 450 here. We can solve for our d. Okay, solve for our d, which is that. So that means this would be our position equation. So from that, if I want to know when it hits the ground, I just set position equal to 0 and solve to where we get this. So it takes 9.8 seconds to hit the ground. Then if we want to know what is the velocity at the moment of impact, well, if that's the moment of impact, we just plug it in for our velocity. We get negative 93.88 meters per second. So if the initial velocity, so then if I throw this sucker down from the top of the building, my initial velocity is negative 5 meters per second. well, then it wants to know when does it hit the ground. Well, we know from class that this is our position function, right? So negative 9.8 and then t squared over 2 plus v naught t plus s naught. Or we could have gotten that just by doing some antiderivatives. If this is v naught and this is s naught, we simply plug those in. That's our position function. Set equal to 0 means that when we use the quadratic formula, you're going to get 9.09 seconds. Double check that using your quadratic formula. Well, now if we have a raindrop that's falling in for the first 10 seconds, that's its acceleration. After that, it's 0. Well, then during the first 10 seconds, that's our acceleration. If I take an antiderivative, I get that for velocity. But they said that our initial velocity was 10, so negative 10 for initial velocity. That means that's going to be our function. If we take an antiderivative, we're going to get this, right? If we clean it up just a second, we get this. And then for S naught, if we know that our initial position is 500, this is our position function. Hey, what's up? I'm finishing a video really quick. I'm almost done. Can you shut the door in the garage door for me? Yeah. Shut the door in the garage door. Thank you. I'm warming up supper. Mom's warming up supper right now. I'm almost done.
Are you done playing with it?
So after 10 seconds,
Hey, come here.
it's okay.
Come here.
After 10 seconds,
Come here.
the position above the ground is that.
Did anyone give you any comments on your cutie patootie dress today?
Right, so So after 10 seconds, there are 100 meters left to fall, right? Because we ended up getting that at time 10, we were 100 meters above the ground. So that means when we look at the equation for acceleration for after 10 seconds, acceleration is 0 means velocity is constant. But after 10 seconds, from our formula, when we put in 10, we end up getting negative 55 meters per second is the velocity. So for the last 10 seconds, if it's constant for the last 10 meters, then that divided by that means that the last 100 meters is 1.8 seconds. So total is 11.8 seconds. Well, then if we've got a car and the acceleration, constant braking of negative 16 feet per second, if this is our velocity, so we do an antiderivative, we get that for our velocity. That means if I solve it for when does the car stop, I set velocity equal to 0, I get that the time this sucker stops is v naught divided by 16. If you think about it, that makes sense. So using an antiderivative, if this is my velocity, if I go back one, this is what I get for position. But if S naught is 0 where I started braking, then this would be my position. So into my position function, I can plug in the time when we stopped, v naught over 16. When I do that and do some algebra, I get v naught squared over 32 is where we stop. But guess what? It said it took 200 feet to stop. So when I set that equal to v naught squared over 32, we end up that it was 80 feet. 80 feet per second. Oh, no, I'm sorry. 80 feet per second was my initial velocity when we solve for velocity. So that's about it. We can talk about that more in class if that did not make sense. These last few were definitely problems and not exercises. Definitely the last two you might not see on an exam. I think that parts of 65 are very doable. And I also think that 62 was very doable. So have a great day.